Hey, welcome back everyone. This is lesson 4 of unit 4. Today we're going to be talking about the mean value theorem. So far we've had two prominent theorems that we focused on. One was the intermediate value theorem, one was the extreme value theorem, and we just covered the extreme value theorem a few lessons ago, but the intermediate value theorem actually was way back from unit 1. So if you need to recall that, go ahead and look back at those videos. But today it's the mean value theorem. And if you think of the word mean also means average. So that's going to play into the idea here. But before we go into actually what the mean value theorem is, let's look at a scenario where we can kind of understand what the mean value theorem is going to do here. So here's a scenario. You're driving down the freeway and you get pulled over by a highway patrol officer for speeding. But at the moment that you were pulled over, you weren't speeding. You were going well under the speed limit at that time. Okay, so after you're protesting and arguing, hey, I wasn't speeding, the police officer says, here's the deal. When you got into the express lane, okay, it recorded a time of 11 a.m. When you got out of the express lane, it recorded a time of 12:30 p.m. So if you've ever been in an express lane, there's these bars that go over it, and it keeps track of who has passed through. If you have a little ticket or something that allows you to go through those express lanes on the freeway, but you entered the express lane at 11 o'clock, and you got out of the express lane at 12:30, and the express lane is 120 miles long. And so that's what he uses as justification for giving you a speeding ticket. The question is he justified in giving you that speeding ticket? And the answer is yes. And here's kind of the idea. You traveled 120 miles in a matter of 1.5 hours, okay? You traveled 120 miles in a span of 1.5 hours. Well, if you do the math there, what is that? That's 240 over 3. That's 80 miles per hour. That's 80 miles per hour that you were traveling on average. And that's the key here. We've talked about average rate in the past and how average rate is related to instantaneous rate, or the instantaneous rate being the derivative. But your average rate is 80 miles per hour over the span of 1.5 hours, okay? Now, you may not have been speeding at the time that he pulled you over, but because your average rate was 80 miles per hour, that implies that you must have been going 80 miles an hour at some time during your travels. And you could also conclude beyond that you must have been traveling at a rate faster than 80 miles at some point within that hour-and-a-half span, because you were traveling below the speed limit at some point. Therefore, you had been traveling above the speed limit at other points to balance out. If let's say our speed limit was 70 miles an hour or 65 miles an hour. But the bottom line is, because your average rate was 80 miles an hour, you must have been traveling 80 miles an hour at a certain point in time somewhere along that path. Unless, of course, you know how to teleport, which I guess is possible. No, not possible. What you would be looking at then is some sort of jump discontinuity on your position graph, right, which is not a thing. So this is the idea of the mean value theorem. The police officer was absolutely right in giving you the ticket, because your average rate was equal to 80 miles an hour, which means your instantaneous rate will be equal to 80 miles an hour somewhere in that interval. That is what the mean value theorem does for us, okay? So let's get into what the mean value theorem actually says. It says if a function is continuous on a closed interval and it's differentiable over the same open interval, then we can conclude that if I find the average rate between 2 points on that graph, then we know, the average slope between 2 points on that graph, then we know that there will be a tangent line somewhere in that interval that is parallel to that secant line. Okay, so that's basically what it's saying. I want you to kind of mull that over, so you probably should read that definition a few times in your brain. But the bottom line is this: if I have a function that is continuous over a closed interval, so I'll take a look at a function that starts whatever point that is, and it increases, and then maybe it decreases, it ends at that point. So this is a continuous function over that closed interval. This function is also differentiable over the open interval there. The reason it's not differentiable at the endpoints is because you can't be differentiable at endpoints, right? But it is differentiable over the open interval because there is no vertical tangents, there is no cusp, there is no corners, there is no discontinuities. So we can say, since the function is continuous over the closed interval and differentiable over the open interval, the mean value theorem is going to apply here. Well, let's try and understand what the mean value theorem actually is saying. It's saying that if you find the slope between the two endpoints of that interval, so we can find the slope of that guy, then there will be a tangent line that is parallel to that secant line. So if we were to draw a tangent line that's parallel to that secant line, it would be somewhere in this region, something like this. I draw that tangent line, I can see that it is parallel to that secant line. Okay? And you might be formulating in your head some ways to provide a counterexample for this. Well, I'll go ahead and talk about a few counterexamples so you can see this, but before we do that, let's go ahead and take a look at another way of saying this, okay? So if f is continuous over the closed interval a to b, so this being a and this being b, okay, and differentiable over that same open interval, then there is at least one point c, so that means there is a point somewhere in here, we'll call it c, okay, some x value c, such that the derivative f prime of c is equal to f of b minus f of a over b minus a. And so that's exactly what's going on here. Since this function is continuous and differentiable over this interval, there is a point c where I can take the derivative, which means find the slope of the tangent line, and that slope of the tangent line will be equal to the slope between point A and point B. Okay, so that's what the mean value theorem says. Here's another look at it on the lesson over here. Okay, so if you look at that, I got a little bit different graph here, but that function is continuous and differentiable. If I find the average slope between point A and point B, I can also find a tangent line that is parallel to that, or I can find a derivative that is equal to that average slope. Okay, so let's go ahead and take a look at maybe some ways that we might want to try and disprove this somehow. Well, if I look at a function and we want to be continuous here from point A to point B, right? And we're drawing a secant line between those points, could I possibly draw a curve so that it does not have a tangent line that's parallel to that? Well, we could maybe argue that, all right, well, what if I draw something that looks like, I don't know, something that goes down like this and then up like this, right? Well, the function is continuous, it's differentiable. Can you see a tangent line somewhere? Can you see a point along this curve, a c value, that will be parallel, or the tangent line at that c value will be parallel to that point? And yeah, you can see it here, so that doesn't prove anything, right? That holds true here. Let's take a look at another graph maybe. Let's say we have a function that looks something like this. I like this one. Let's see. So there's the curve, right? If I were to draw a secant line between those two endpoints, right? Could we find a point in that open interval that would produce a tangent line parallel? Well, in this case, it would be very difficult to do so. But you'll notice that we have a problem here. The reason it's difficult to find a tangent line that's parallel to the secant line is because the mean value theorem states that the function must be continuous, this is, over that closed interval, but it must also be differentiable over that same open interval. And we can see that this function, in fact, is not differentiable because we have a corner at that point there. So in this case, the mean value theorem just does not apply because the hypotheses of that mean value theorem are not met. It is not differentiable. Okay, so kind of wrap your head around that idea of the mean value theorem, and then we'll go ahead and take a look at what that looks like in an example problem here. So taking a look at this example, does the following function, so we have f of x equal x squared plus 2x minus 1, okay, f of x equals x squared plus 2x minus 1, okay, and we're looking at the interval x within 0 to 1. Okay, so we're looking in that interval. The first question is, does this satisfy the mean value theorem? Well, for it to satisfy the mean value theorem, two things must be true. It must be continuous over the closed interval 0 to 1, and it must be differentiable over the same open interval 0 to 1. So we would look at this function. We see that this is a nice, easy parabola. We could say that this parabola is always continuous, so it is continuous over that closed interval. A parabola is also differentiable over any interval. Okay? So therefore, we would say, yes, the mean value theorem applies. So since both those things are true, we could say the mean value theorem applies. Okay? As a result of that, that implies that the average slope in the interval is equal to the derivative for some value, some x value within that interval. Okay? So it says identify the point at which the tangent to the graph has a slope equal to the average slope over the given interval. Now, oftentimes with students doing these kind of problems, really in calculus in general, we read it, but we don't understand what it's telling us to do. But if you read carefully, it's giving you a step-by-step instruction on what to do. It says identify the point at which the tangent to the graph has a slope equal to the average slope over the given interval. So the first thing I want to do is I want to notice that we are going to need to find the average slope over the given interval. Well, how do we find the average slope over an interval? Well, to find the average slope, remember the average slope is we're going to use f of b minus f of a over b minus a, right? And sometimes we'll say f of x2 minus f of x1 over x2 minus x1. But I use b minus a because that's how the mean value theorem is written here. Okay, so what we're saying, since the mean value theorem applies, we're saying that there is a derivative at some x value that is equal to the average slope. So we need to figure out these things. We need to figure out the average slope, and we need to figure out the derivative. So I'm going to go ahead and figure out the average slope here. The interval is from 0 to 1, so we'll say that f of 1 minus f of 0 over 1 minus 0. So this is my average slope here. If I plug in 1 for f of 1 is going to be 1 squared, which is 1, plus 2 times 1, which is 2. So 1 plus 2 is 3, minus 1 is 2. So we get 2 minus f of 0, that's going to all cancel out. We're left with negative 1 there. All over 1 minus 0 is 1. So our average slope here is just 3. So we're saying that the average slope over this interval is 3. Now, if we looked at a graph of this, we can kind of map it out and visualize it, but we're not going to do that right now. Now, we found the average slope. Now we need to find the place where the tangent line to that graph has the same slope. Well, how do I know when a tangent line has the same slope? Well, the slope of a tangent line is the derivative at a point. So I'm going to go ahead and find the derivative here. So we would say that f prime of x is equal to 2x plus 2, because we're using the power rule and the addition rule here. So the derivative is equal to 2x plus 2. And our goal is to figure out when the slope of the tangent line, in other words, when the derivative is equal to the average slope. So if we want the derivative to equal the average slope, it's as simple as setting these two expressions equal to each other. So we'll end up with 2x plus 2 equals 3. And then solve this, so we end up with 2x equals 1. So x equals 1/2. And so what x value has the tangent line having the same slope as the slope over that interval, and that would be when x equals 1/2. Okay, so what I want to do is kind of give a rough graph so that we can see what's going on here. So if I graph this parabola here, finding the vertex or finding the minimum, if you want to say that, the minimum is going to end up being negative b over 2a. That's going to end up being -1. And then when I plug in -1, I end up with -2. So we have a vertex of -1, -2. And we can kind of follow, let's see, the slope pattern here. So we have a parabola that kind of looks like this, okay? That's the graph of the parabola, okay? So what we did is we said the slope, the average slope between 0 and 1, so from x equals 0 to x equals 1, we found this average slope here. So we've got this secant line with this slope. And I know that this is really hard to see, but it's saying that when x equals 1/2, so if I go over half and I draw a tangent line, I can kind of see that those two lines will be parallel to each other. So that's kind of rough to see, but that's kind of the graphical representation of what's going on. Okay, so that's kind of the idea behind using the mean value theorem to find an instantaneous, or a place where the instantaneous rate is equal to the average rate. The reason the mean value theorem is so important is because when we start applying calculus to real life, we don't necessarily deal with nice clean functions. What we start dealing with is a lot of numerical data. So we'll be looking at tables. And if we're looking at tables, we can't really find exact derivatives. We can only find average rates. But if we know that these functions are going to be differentiable, because we live in real life and there's no such thing as time travel and things like that, we know these functions are going to be differentiable somehow. That would imply that if I can find the average rate between 2 points on a data set, then I will know that the derivative will be equal to that slope somewhere between those two data points. And so we'll see more examples of that as time goes on. But again, just a quick recap of this. We first wanted to see if the mean value theorem applies, so we checked to see if the function is continuous and differentiable. It is. So therefore the mean value theorem applies. Then we can find the average slope. The average slope is f of 1 minus f of 0 over 1 minus 0. We work that out, we get 3. And then we're looking for the tangent line to have the same slope. Well, in order for that to be true, you take the derivative, and the derivative represents the slope of the tangent line. So we set that value, or that function, equal to the average slope. So we'll set it equal to 3, and we end up with x equals 1/2. And then when I plug in 1/2, because it says identify the actual point, if I plug in 1/2 back into my function, because I want to find out where that occurs, I end up with 1/4. So the actual value, the actual coordinate point is 1/2, 1/4. Okay? So let's go ahead and take a look at a couple other examples to see what this looks like in a couple different scenarios. So for this first one here, same question. First, we have to figure out if the mean value theorem can be satisfied. So to do that, for number one, we have a piecewise function here. So remember, for the mean value theorem to work, the function must be continuous over the closed interval and open, and differentiable over the open interval. So I'm going to go ahead and write this down. We've got f of x equals some sort of piecewise function here. We've got x cubed plus 3, and that's for the interval x is less than 1. And we have another function, 2x squared, or another piece of the function, 2x squared plus 2, for x is greater than or equal to 1. And we're looking over this interval, this interval of -1 to 2. So in order to find out if the mean value theorem applies, we have to check for continuity first. And if you remember way back, to find out if a function is continuous at a well, this function is continuous everywhere. This function is continuous everywhere. So the only question where we might not have continuity is at x equals 1, because this is a piecewise function. So for every value to the left of 1, we're continuous. For every value to the right of 1, we're continuous. Now we have to check to see if we're continuous at 1. So we're going to try and figure out if the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right, and we have to see if that equals f of 1. So those are the three things we have to check here. If I find the left-hand limit, we're going to plug in 1 here, so we get 1 cubed plus 3, which is 4. If we find the right-hand limit, that's going to be 2 times 1 squared plus 2. That's going to end up being 4. And then if I plug in f of 1, I'm going to use that bottom one again. We end up with 4. So indeed, all those three things are true. Therefore, the function is continuous over -1 to 2. Okay? So now, the next thing we have to do is find out if it's differentiable over that same closed or open interval. So to find out if it's differentiable, we have to check to see if the left-hand derivative at 1 equals the right-hand derivative at 1. So we're going to go ahead and take the derivative of that function. So the derivative of a piecewise function is also piecewise. The derivative of the top part is going to be 3x squared, and that's going to be for x is less than 1. The derivative of the bottom part is going to be 4x, and that's for x is greater than 1. So those are the derivatives. Now, if I evaluate f prime of 1 from the left, we want to see if that is equal to f prime of 1 from the right. So this is a question mark here. Is that true? Well, f prime of 1 from the left, we're going to plug this guy in. So that's going to be 3 times 1 squared, which is 3. And then f prime of 1 from the right, that's going to be 4 times 1, which is 4. So obviously those things are not equal. So we would conclude that f is not differentiable over -1 to 2. As a result, if the function is not differentiable over that open interval, we would have to conclude that the mean value theorem does not apply. So we can't do anything to find a tangent line that would end up having the same slope as the average slope. So we would just say it's continuous, but it's not differentiable, so the mean value theorem does not apply in that case. Okay? So for number two, we don't have a piecewise function. We have f of x equals x to the 2/3. And we're looking to see if the mean value theorem applies over the intervals 0 to 1. Well, the first thing I note here is that f of x is a continuous function. Because that's a cube root, any x value that I plug in, whether it be negative or positive, I'm going to get a value out of it. I'm not dividing by 0 anywhere, so this function is in fact continuous over 0 to 1. So that's a true statement there. We can check that off as something that's true. Now we need to check differentiable. So we're going to take the derivative here. So f prime of x is equal to 2/3 times x to the -1/3. Okay, Well, I don't like dealing with negative exponents. I don't know of many people that do. So we're going to rewrite this as 2 over 3x to the 1/3. So that's our derivative. So we have to ask ourselves, is this function differentiable over this interval? Well, what are two things we're not allowed to do in math? We're not allowed to divide by 0. We're not allowed to take the square root of a negative number. So I would be dividing by 0 if x is 0 here. So we would say f prime of x does not exist when x equals 0. Because if x is 0, I plug that in, I get f prime is 2 over 0, which is infinity if we're talking about limits. So we either have a cusp at this point or we have a vertical tangent. But either way, we don't have to worry about that because we need the function to be differentiable over the open interval 0 to 1, not the closed interval 0 to 1. So it's not differentiable at 0, but that is not part of the interval that I'm looking for differentiability. So in fact, it is differentiable over that interval there. Since both of these statements are true, we can conclude that the mean value theorem applies. Okay? So that's the first step in this process. Now, the next question says, if so, identify the points at which the tangent to the graph has a slope equal to the average slope. Okay? So I need to find the average slope here. So the average slope, we're going to say average slope is equal to f of 1 minus f of 0 over 1 minus 0, which is, if I plug in 1 there, I end up with 1. If I plug in 0, I end up with 0. That's over 1 minus 0. So my average slope is 1 over that interval. Okay? Now, I need to take the derivative. Well, I already did take the derivative here. So this is the derivative. Actually, I'm going to use this guy because, again, I don't like negative exponents. Where is the tangent line slope equal to the average slope over that interval? So we're going to take that derivative, 2 over 3x to the 1/3, and we're going to set that equal to the average slope. So we're going to set that equal to 1. So when we go to solve this, we'll cross multiply here, if that's how you want to look at it. We end up with 2 equals 3x to the 1/3. We'll divide by 3 here, so you get 2/3 equals x to the 1/3. And then to get x by itself, we have to get rid of that 1/3 power. So we're going to raise this guy to the 3rd power. And we're going to end up with 2 cubed is 8 and 3 cubed is 27. So we know that the tangent line has a slope equal to the average slope over this interval at x equals 8 over 27. Now, we're going to go back and plug that point in to f of x to actually get the y value out of that. So f of 8 over 27 is equal to 8 over 27 raised to the 2/3 power. So I'm going to go ahead and take the cube root of 8. The cube root of 8 is 2. Square that, that's 4. The cube root of 27 is 3. Square that, it's 9. So our final answer is going to be 8 over 27, comma 4 over 9 is the coordinate for which the average slope is equal to the slope of the tangent line in that interval. And we can verify that 8 over 27 is in fact between 0 and 1. Okay? All right, and there is our answer, 8 over 27, comma 4 over 9. Okay, so those are 3 examples of how to apply the mean value theorem in one aspect. I have one more slide here that I want to talk about, and it's incorporating a lot of stuff from calculus. So let's go ahead and take a look at this next question here. We have a function that is continuous over the closed interval -2 to 3, and it's differentiable over the open interval negative 2 to 3. So right there, it should be causing you to think, okay, we just learned about this mean value theorem. The function is continuous over the closed interval. It's differentiable over the open interval. Therefore, the mean value theorem applies. So here's some data for us to look at. We've got x and f of x. And we have two data points here. So when x is negative 2, then f of x is 17. And when x is 3, f of x is 5. So we have this data set of data here. Now it says, which of the following statements could be false? Well, in option A, it says there exists a c value within that open interval such that f of c is equal to 10. Well, first of all, I would note that when it says f of c is equal to 10, that implies that c is an x value. So let me reread this. There is an x value within this interval where the y value is equal to 10. Well, I can kind of get an idea of what's going on here by graphing this. If I graph negative 2, 17, okay, and if I graph 3, 5, all right, so those are the two ends. Now I know that this function is continuous and it's differentiable over that interval. So the point is here, do we have some value in between negative 2 and 3 that will produce a height of 10? And so 10 is somewhere in between 5 and 17. And so we should recognize this from way back. This is the intermediate value theorem at play. If the function is continuous, it just has to be continuous, it doesn't have to be differentiable. If the function is continuous, then the function must pass through every y value between 5 and 17 within this interval. It can pass through other points that are higher than 17 and lower than 5, but it must pass through every point between 5 and 17. If I got to connect these dots, I got to pass through every point in between, and 10 is one of those y values. So therefore, option A is a true statement, and that is by the intermediate value theorem, okay? B, it says there exists within the interval negative 2 to 3, f prime equal to negative 12 over 5. So now we're talking about, in option A, we were just talking about the y value, f of c. Now we're talking about the derivative. Well, the derivative is dealing with the mean value theorem. And so let me take a step back because I didn't really dive into this too much. But when you say mean value theorem, you're actually saying the average value theorem, because mean is synonymous with average. So if you're looking at the average value theorem, okay, we're looking for the average rate, and the average rate will be equal to the derivative somewhere. Okay, so if I'm to find the average rate between these 2 points, the average rate or the average slope is going to be equal to 5 minus 17 over 3 minus negative 2, which is negative 12 over 5. So the average rate is negative 12 over 5, which implies that the derivative must be negative 12 over 5 at some point in between these 2 points. That's exactly what the mean value theorem is saying. So that's a true statement also, and that's by the mean value theorem. For option C, it says there exists within the closed interval, negative 2 to 3, some x value for which f of c is greater than f of x. Now, the way this is written gets kind of weird. I mean, it just gets, honestly, kind of hard to understand here. But the bottom line is, it's stating that there is some x value between these 2 points where that point, f of c is greater than f of x. Well, f of c is a specific point on the graph of f, and f of x is the function in its entirety. So we would say that f of c is going to be greater than all the other points somewhere over that closed interval. So we can look at it this way. No matter how you connect these dots, because it's continuous, no matter how I connect these dots, if I just go like this, is there an x value that's higher than all the other, is there a y value that's higher than all the other y values? And the answer is yes here. This is the highest value. Well, if I drew the graph, I'll use a different color here. If I drew the graph so that it went up and then down, is there a y value that's higher than all the other y values? Yes, it's right here. If I drew the graph just to connect it so it goes, maybe it goes down and then up and then down, however we draw it, is there a y value that's higher than all the other y values? Yes, in this case, it's here, because we're looking at the closed interval there. So this is actually called the extreme value theorem, right? There is a point on a graph higher than all the other graphs if the function is continuous. But there is one typo here. Because f of c is not greater than all f of x, we would say that f of c is actually greater than or equal to f of x. So if I fix that typo there, that would also be a true statement, and that's by the extreme value theorem. And if I look at option D, it's the same thing, but now we're looking at the opposite of this. We're saying, is there a y value that is less than all the other y values? And we can look at these examples to get an idea. If I'm looking at the blue graph, then this endpoint is the lowest y value. If I look at the orange graph, then this endpoint is the lowest y value. If I look at the purple graph, then this point right here, at 0 maybe, is the lowest y value. It is lower than all the other y values. But again, we need to say that it's less than or equal to all the other y values, because you can't have a point that is we can't have a point on the curve that is less than all the other or less than any point on the curve, because it's on the curve itself. So it has to be less than or equal to. So again, that would be a true statement if we correct those two typos there. And you can see that I did that right here. You can see that I put the little lines here to say equal to. So if that correction is made, then we could say that all of those statements are true statements, which means none of them can be false. So that's the lesson on the mean value theorem. There's a lot more application that we can do the mean value theorem. We can apply the mean value theorem to. We will get more into that into the future. But for now, that's it. Have a great night or day or wherever you're at, and I'll see you next time.